All right, so let's start. Last time I wrote this proposition, and I guess we proved it, half of it. So a space X is simply connected. If and only if for any 2 points, x0 and x1 in X, and 2 paths joining 2 paths, let's say gamma 1 and gamma 2, joining x0 to x1. There is a homotopy from gamma 1 to gamma 2, keeping the endpoints fixed at all times. Okay. Fena gözükmüyor. Kötü. Okay. We did this part. So if it is simply connected, no, we did this part. Okay. It's done last time. This was kind of the easy part. For this part, we proceed as follows. Now assume that X is simply connected. What we have to do the following. We have to find a homotopy from, let's say, gamma 1 to gamma 2, or gamma 0 to gamma 1 mı demiştik? Geçen sefer öyle dedi sanırım, değil mi? Gamma 0 to gamma 1. Öyle ki homotopinin her adımı, any step of the homotopy, so gamma t will be just f, gamma t s will be just f s t. Okay, so any time t map of the homotopy will keep these endpoints. Okay, so gamma 0 is homotopic to gamma 1 through paths from x0 to x1. Okay. This is easy, but one has to be a little bit careful. Okay. So we have to prove, that there is an homotopy, so that this end is gamma 0, this end is gamma 1, this side is x0, and this side is x1. Okay. Now we proceed as follows. Since X is simply connected, the path gamma 0 to gamma 2, gamma 1 inverse is homotopic to the constant loop at x0, right? Because, here is x0, here is, let's say, gamma 0, gamma 1. Gamma 1 bar is the inverse path. So the composition is a path from x0 to x0. And since x is simply connected, any path at x0 is homotopic to the constant loop. Okay. So there is a homotopy G from I cross I into X, given by, a diagram like this. Here it is first gamma 0 and then gamma 1 bar. This side is x0, this side is x0 and this side is x0. Değil mi? Sabit pete bir homotopi var. Şurada da G var. Böyle yazınca bu G'nin açık, yani daha doğrusu şeyini yazmak kolay değil mi? İşte G bu kenarda bu ikisinin kompozisyonu, diğer üç kenarda da sabit. Peki, now bizim istediğimiz şey nedir? Böyle bir homotopi. Bunu kullanarak şuna geçmeyi istiyoruz. Burada okey, neyse, yani şöyle bir şey yapacağız aslında. Neyse yapayım da daha açıklaması daha kolay. We construct a simplicial homomorphism by as follows. Şöyle bir map tarif edeceğiz. Şurada x0, o x0, x0. Şimdi şurası gamma 0. Burası gamma 1 inverse. Ondan sonra şöyle bir şey yapacağız. Böyle. Burası gamma 0 olacak. Burası gamma 1. Dolayısıyla ters yönde giderseniz gamma 2. Ondan sonra da şunlara isimler vereyim. Şurası bir kenar olsun. Bunun yönü şöyle olsun. Şurası 2 olsun. Burası 3 olsun. Burası 4 olsun. Şu da 5 olsun. Şimdi o doğru parçalarını şöyle map edeceğim. Şimdi mavi olana 1 dedik. 1 şurası. Mor olan 2. Turuncu olan 3. Bu 4. Bu da 5. Şimdi bakın. You see, we have several triangles here. For example, consider this triangle. Okay. One side is gamma 0, and then I have 1 and 5. Gamma 0, 1, and 5. I'll choose my homeomorphism, okay, so that it will map this triangle to this triangle, and it will be linear. Well, actually, I should say maybe affine map. Mapping, you know, these corners to these corners. Once you specify the images of these corners, then the map will be defined linearly. So this will be a piecewise linear map, okay? It will map this triangle to this triangle, and then the triangle 1 to x0. 1 to x0. So this side will be mapped to x0, all of it. And yeah, okay. Böyle bir şeyi nasıl yazarsınız? Bir tane örnek vereyim isterseniz. Hani so this okay. Once the corners of each triangle is specified, the map is uniquely determined. İsterseniz şurada bir tane yapayım. Bir örnek. Mesela şöyle diyelim. Efendim? Evet. Şimdi onu açıklayacağım neden olduğunu. Mesela x1.
Hocam, your video is not completely in focus. Can you recalibrate that?
Yeah, okay, sure. Is this better?
Yes, sir.
Okay.
Sir, can you also reread the last sentence, starting once the corners of what triangle?
Yeah, okay, I'll do that. So once the corners of the of each triangle is specified, so what I mean, consider this triangle, okay? These are the three corners. This will be mapped to where? It will be mapped to this triangle. So the H5 will be mapped to this, the H1 will be mapped here, and so on. So I specify that this point is mapped to this point is mapped to this one, and this one is mapped to this one. Once I specify where these corners are mapped, the rest of the map is uniquely determined. How? Let me just explain this on an example. Okay, so here is y0, let's say y1, y2. Okay, 1, 2, 3 diyeyim. Şöyle. Şimdi bir şöyle order etmiş olayım. Şimdi bunları so we are in the plane. This map is okay. Now any point here in this triangle, okay, any point here P has so-called barycentric coordinates. So this P can be written in a unique way as follows. This is just lambda 1 times x1. So I just considered x1, x2, x3 as points in the plane. They have we have a coordinate system. So that these are all between 0 and 1, and they add up to 1. Okay, there is a unique choice of lambda 1, lambda 2, lambda 3. So any point here can be written like this. Takip edin. Oh, okay. Şöyle diyorsun. So if you connect, okay. Okay. So once I specify the images of x i's, then the image of phi at P is defined to be how? Well, image of x1, and then you just multiply by lambda 1, lambda 2 times this, and lambda 3 times this. This lambda i's, by the way, are called barycentric coordinates of the point P. Okay, so these are barycentric coordinates of P with respect to x1, x2, x3. Dolayısıyla all you have to do just decide where these points are mapped. So in here, in this picture, you just specify all these points, their images, okay? And then in each triangle, you apply this method, okay? So on each triangle, you have an expression like this. This is not as global map. It is defined on each triangle, but it will be automatically continuous because on each edge, it will be defined by the same formula, okay? Because the endpoints are mapped to the same points. I mean, on this triangle and on this triangle, these points are mapped to these points. wherever they are. So it will be continuous, but it will not be differentiable. So it's a piecewise linear map. Okay, so to speak. Bunu herkes şey yapabildi mi? So this map is a homeomorphism. Okay, this map is a homeomorphism, and you just let now. Okay, now let H to be this homotopy composed with this homeomorphism, and finally we define the required homotopy F using the diagram below. Well, the thing here, which is not good, this map is not defined on a rectangle. It is defined on a triangle, but our homotopies are defined on rectangles. So we have to modify this picture a little bit, and this is how we do it. Okay, now we have gamma 0 here, gamma 1 here, x0 here. This point was mapped to x1, this point. So my h is defined only on this lower triangle. But then we do the following. We just define our map to be x1 on this h and gamma 1 on this h. Actually, it is gamma 1 on each of these lines. Okay, on each of them, it is gamma 1. Of course, you know, it will not be the same formula because, you know, they are defined on different line segments. How can you do this? You can define your map to be constant on each vertical line segment. The value of h at this point was, you know, something gamma 1 of some value. I just use that value on this line segment, vertical segment. Dolayısıyla burada şuradan başlayıp buradaki noktada biten bütün şeylerde fonksiyonumu gamma 1 olarak tarif ediyorum. Dolayısıyla ne elde etmiş oluyoruz? So this whole homotopy is a homotopy from gamma 0 to gamma 1, which is x0 on this h and which is x1 on this h. Tamam mı? Yani böyle küçük numaralar var şeyde algebrik topolojide. Buradaki yalnız şu şey fikri çok önemli. Bunu kullanacağız. Simply connected olmanın. So this you know, remark is very important. Let me write it one more time. So a space X is simply connected if X is path connected, and any two points are connected by a unique path up to homotopy. Keeping the endpoints fixed. This is a very strong, idea. Let me tell you a little bit how we will use this. So if your space is simply connected, then you can do the following. Fix a point here, then any other point in the space actually is characterized by a homotopy class of a path joining this point to this point. So instead of listing the points, you can just list the paths starting at x0, ending somewhere, and then you consider homotopies that keeps the endpoints fixed. Okay, each homotopy class represents a unique point in the space. Therefore, you can represent your space as equivalence classes of some set of paths. Yani uzayınızı petlerin bir kümesinin equivalence class'ları üzerine tanımlı bir equivalence relation, equivalence class'lar olarak görebilirsiniz. Bu da bizim çok kullanacağımız bir construction'ı verecek. Peki. Okay. Aslında şurada söyleyeyim. Mesela şu uzay simply connected değil mi? Example. R2 minus the origin is not simply connected. So if you delete the origin from the plane, this is not simply connected because, as we talked, I guess last time, from this point to this point, there are several paths and they are not homotopic, right? This path is not homotopic to this path. We will see why it is not soon. And therefore, for these 2 points, there is no single homotopy class of paths joining these 2 points. That's why it is not simply connected. It is multiply connected. This is one way of going from this point to this one. This is another one. This is another one. This is another one, and so on. So we have several different ways of going from one point to another. Okay, so here is the definition. A map F from X to Y is called a homotopy equivalence. if there is a map G from Y to X, so that first G composition F is homotopic to identity function of X, and second, F composition G is homotopic to the identity function of Y. Okay? Neither F or G needs to be an homeomorphism. Okay? They are just continuous paths, so that the compositions are homotopic to the identity functions. Okay. One quick remark is that, I say this is an homotopy equivalence, so I kind of give the hint that this is a homotopy equivalence. This is an equivalence relation, and it is really the case. Being homotopy equivalent is an equivalence relation. So if two spaces are homotopy equivalent, well, in this case, of course, if there's a homotopy equivalence, maybe I should say, in this case, we say that X and Y are homotopy equivalent. Okay. Being homotopy equivalence is an equivalence relation on the collection of all topological spaces. Okay. This is much weaker than being, homeomorphic. It's a very, rough classification of spaces, but in some cases, in some special classes of topological spaces, being homotopy equivalent is equivalent to being homeomorphic. Let's see some examples. Bu arada şey de söyleyeyim, belki şurada ekstra bir tanım. Yok, o doğru değil herhalde. Şöyle diyeyim, tamam, bundan vazgeçtim. Ben contractible uzay nedir diye söylemedim değil mi? Daha önce öyle bir şey tarif etmedik. Example. Ya da tanım vereyim. A space X is called contractible contractible to a point x0 if there is if aslında there is demeyeyim, the constant map, let's say phi from x to x0 yok. Şöyle diyeyim. Pardon. If the identity map okay, is homotopic to the constant map. Buna C diyeyim isterseniz, şöyle C constant map C x0 for all x constant pt homotopics. Bu homotopinin her adımında da x0'a götürmesi gerekiyor mu? Çok emin değilim. Neyse, onu kontrol ederim. Okay. Examples of homotopy equivalent spaces. If X is contractible, to a point, say x0, then X and this point are homotopy equivalent. Neden? Şöyle görebiliriz. Şu fonksiyon inclusion fonksiyon olsun. Inclusion map. Yani x0'a götürüyor. C'de constant path, constant function. O zaman bunların kompozisyonlarına bakarsak, burada galiba şey demem lazım. Homotopic to constant map by a homotopy mapping keeping x0 fixed. Yani homotopinin de her adımda x0 noktasını sabitlediğini kabul etmem lazım. Yoksa bu doğru olmuyor. Şimdi şeye bakalım. F'i şöyle tarif edeyim. Define F x cross i'dan x'e şöyle tarif edilsin. X0 for all x in x. Şimdi contractible olduğuna göre elimde böyle bir f var. Yok, buna define demeyeyim de let so this is the homotopy from identity function of x to the constant function. Şimdi contractible dedik ya Uzay. Contractible olunca şu var. X cross I'dan X'e bir map'im var. T eşittir 0 anında fonksiyonum identity of x. T eşittir 1 anında fonksiyonum constant path c. Yani her yerde x 0 değerini alıyor. Ve de tabii ki x0 noktası da her adımda sabit kalacak. Yani şunu da biliyorum. Onu da belki söylemek lazım. F x0 t'de her zaman x0 eşit. Bütün t'ler için. Şimdi o zaman şuna bakalım.
Sir,
Yes.
I'm a bit confused about what you mean by the identity path here. Does it mean any arbitrary path or something else?
Identity function. So identity of x is the identity function on x, taking x to x for all x. So identity function is homotopic to the constant function. Okay.
Why is this not the same homotopy as taking any arbitrary path to the constant map? Because any arbitrary path is embedded in the space, and if we can
No,
take the
here
identity.
we are not talking about paths here. I mean, this is a homotopy of functions, not just paths.
Okay, sir. Thank you.
Now, if there is a homotopy like this from the identity function to the constant function, then our space is contractible. And in that case, I claim that our space is homotopy equivalent to the one-point set consisting of x0. Why is that? Because you see now I have this inclusion function taking the single point to x0, and we have the constant function taking every point to x0, right? Now, let's consider this composition. I composition C. So this is the map from x0 to, first I go by I to x, and then from I to, again, this thing. And of course, this is the constant path. I mean, constant function. So this is, therefore, this composition is just identity function of this space. Okay. On the other hand, this one, this is from x to x, but it takes everything to the, of course, x0. And I know that this function is homotopic, to the identity function of x via the homotopy f. Therefore, these two spaces, okay, are homotopy equivalent. Burada. Hence, x and x0 are homotopy equivalent. Okay.
Sir, earlier you said C composition I is equal to identity on x0. Is that equal to or homotopy equivalent to? I didn't quite understand that because the domain over there is all of x, right?
Which one?
C composition I.
C composition I. No, it is domain is just x0. I is from x0 to x.
All right, sir. My apologies.
Nasıl?
Anladım hocam. Teşekkürler.
Evet, zaten bir tane nokta var burada. x0, onu da x0'a götürüyor. Uzayın içindeki aynı noktaya götürüyor. Inclusion fonksiyonu. Right? I is the inclusion function. A typical example of contractible spaces are what? For example, Rn, okay, for any n is contractible to any point. How? What is the contraction map? So I have to write down the contraction map. Just so I map every point to x0. I can actually write down even the homotopy. Rn. So at time 0, it is just, okay, let me just write it this way. It is just 1 minus t times x plus t times x0, okay? You see, when I plug 0 here, I get x. So this is just the identity function of Rn at x. So at time 0, this map is just the identity function of Rn. And the time 1 map, time one map. So when I plug t equals 1, I get 0 here and just 1 times x0 here. So it's this one for all x in Rn. And f is the identity, f is the homotopy from identity function to the constant function. Note that f is the homotopy, is the required homotopy from identity of Rn to the constant function P from Rn to x0. Okay. Bir başka homotopy equivalence'tan bahsedeyim. Pardon. Another example of homotopy equivalence. X equals Rn minus the origin. I subtract 1 point from Rn. Is
Sir,
homotopy equivalent?
before you start this example, can we take a break?
Yeah, sure. Okay, yes. Okay, let's have a break.